Welcome back to the course on plasma physics and applications. In the last module, we have learned the fundamentals of magnetic reconnection. Through this process, a large fraction of magnetic energy goes into particle acceleration and plasma heating. Magnetic reconnection is probably one of the most important mechanisms that heat the solar corona at the temperature of the order of 1 million degrees Kelvin. Magnetic reconnection also plays a fundamental role during coronal mass ejections, which release a huge amount of energy and plasma from the Sun. In this module, which is the last module on plasma astrophysics, I will describe how, from a hot plasma atmosphere, the solar wind can blow. We will use a simple MHD description to derive estimates of the solar wind speed, and we will see how the solar wind can shape the magnetosphere around the Earth. The first hints of the solar wind came in the early 19th century, when the Birkeland suggested that a continuous particle emission was coming from sunspots. This was to explain the observed correlation between auroras and sunspots. About 30 years later, Chapman and Ferraro suggested that particles were emitted from the Sun only during solar flares, and otherwise the space between the Sun and the Earth was empty. The first real evidence of the solar wind came from comet tails. In 1951, Biermann observed that the cometary tails point directly away from the Sun regardless of the comet's velocity. It conjectured that this must be due to ionized gas pushed away by the solar wind. An example is given by this picture here that shows the comet Hale-Bopp viewed from Los Alamos in New Mexico, USA. As you can see, the comet has two distinct tails. The white tail is a dust tail driven by light pressure, and it points away from the Sun. The blue tail, instead, is an ion tail which is driven by the solar wind. It is not radial with respect to the Sun, as the comet has about 1/10 of the speed of the solar wind. The first measurement of the solar wind came from the Mariner 2 mission that was launched on the 27th of August 1962. The Mariner 2 provided 3 months of continuous solar wind data while traveling towards Venus. It measured solar wind speed between 300 and 700 kilometers per second. This was the first experimental proof of the existence of the solar wind. More recent data have been provided by the joint ESA-NASA mission Ulysses that was launched on the 6th of October 1990. As shown in this picture, Ulysses was launched towards Jupiter, where, using the slingshot effect provided by the gravity, it entered a polar orbit around the Sun. Ulysses performed 3 sets of polar passes. The radial plots shown here show the solar wind speed combined data from all 3 of Ulysses' polar orbits of the Sun, each of which takes approximately 6 years to complete. Ulysses was equipped by an instrument called SWOOPS that stands for Solar Wind Observations over the Poles of the Sun. This instrument was designed to provide measurements of the solar wind speeds. The first orbit occurred during a period of solar minimum as indicated by the sunspot number. Ulysses measured a slow wind over the equator of the order of 200 km per second and fast wind over the poles of the Sun of the order of 700 km per second. The second orbit of Ulysses corresponded to a period of maximum activity, as shown by the sunspot number here, between 1998 and 2004. During the second pass, fast and slow winds were measured at all latitudes, consistent with a solar maximum activity. Ulysses has then completed more than 3/4 of the third orbit, as you can see here, occurring around the solar minimum cycle. During this last cycle, Ulysses also gathered informations indicating that the solar wind was about 25% less powerful than it was in the previous solar minimum cycle. So far, we have reviewed experimental data of the solar wind. We will now derive a simple model in which the pressure imbalance between the Sun and the interstellar medium drives the wind. Historically, this was the first theory that was developed by Parker in the early 50s, which allows to derive many important results. However, the fluid description does not take into account kinetic effects, which turn out to be important to describe the solar wind, and therefore more refined theories would be required. Now, let's derive the fluid model. Let's make the assumption of spherical symmetry, and let's use a spherical system of reference where we indicate the position of the solar wind with respect to the center of the Sun that by the distance that we indicate with r. Let's make the assumption that the solar wind has a velocity vr, which is purely radial, and which is a function of the distance r. The plasma in this region is characterized by a pressure P, a temperature T, and a density ρ. Let's use the mass conservation equation and the equation of motion, which we write in the following way, where Fg is the gravitational force due to the mass of the Sun. Let's make the further hypothesis that the acceleration due to the Lorentz force can be neglected and therefore drop the J cross B term. As we said at the beginning, we are using a spherical system of coordinates, and we have also assumed spherical symmetry, such that every parameter is only a function of the radial distance from the Sun, for example, the velocity of the solar wind. Let's make a further hypothesis and let's look for a stationary solution by imposing that the time derivatives are equal to 0. We can then write the mass conservation equation and the equation of motion in the following way. Where g is the gravitational constant and m�sun is the total mass of the Sun. Let's now look for a hydrostatic solution by making the hypothesis that the wind has 0 velocity. By dropping the radial velocity in the previous equation, we can write the equation of motion we can then assume that we can treat the plasma in the solar wind as an ideal gas and therefore using the ideal gas law for protons plus electrons. In this formula, Kb is the Boltzmann constant and mu is the mass of a proton divided by 2, which is the average mass per particle. Using the ideal gas law, we can therefore write the equation of motion in the following way. Let's now make a further simplifying hypothesis, and let's assume that the plasma is isothermal everywhere. If we now define a radius r0, where we know that the plasma has a pressure P0, we can integrate this equation between r0 and r, where the temperature T can be taken out of the integral since we have assumed that it doesn't depend on the radius r. Now, this formula provides the value of the pressure at a certain distance r from the Sun provided that we know the starting pressure P0 and the starting radius R0. Let's see what happens if we consider the pressure at infinity. This term will go to zero, resulting in a finite pressure at infinity, which is a non-physical result. We can therefore conclude that looking for a hydrostatic solution has led us to a non-physical result. Therefore, the hypothesis that the solar wind speed is equal to zero doesn't work. Let's now go back to the original equation of motion and let's look for a hydrodynamic solution by dropping the hypothesis that the solar wind velocity is equal to zero and therefore allowing a finite velocity. We can write down the equation of motion and make, as before, the assumption of an isothermal plasma. We can write down the ideal gas law, as before, and use the conservation of mass. We have to remember that for an isothermal gas, we can define the sound speed as the derivative of the pressure with respect to the density. Using these expressions and plugging them back into the equation of motion, we note that this factor has the units of meters, and therefore we can define a critical radius RC equal to the gravitational constant times the mass of the Sun divided by 2 times the sound speed square. Therefore, we can cast the equation of motion as where we have introduced the critical radius RC. Let's now see which are the consequences of this equation. For small radii, 1 minus the critical radius divided by the radius is smaller than 0. And at the same time, if we suppose that the starting velocity of the solar wind is small compared to the sound speed, we can also write that, therefore, this term and this term in these equations are both negative, which results in a dV over dr, which is positive. This means that the plasma that starts at a certain velocity accelerates, and therefore a wind blows. Now let's try to identify families of solutions of this equation in the RV space as drawn here. On a velocity versus radius plot, let's identify the critical radius RC and the sound velocity Vs. If the solar wind starts at a certain velocity V0 and it reaches the sound speed at a radius which is smaller than the critical radius, dV over dr will go to infinity, and this is a not physical solution which is outside the scope of this simple fluid treatment, which would result in a trajectory schematically drawn here. The second family of solutions is represented by a wind that started at initial velocity V0, accelerates up to a certain maximum velocity at the critical radius RC. Now, if this maximum velocity is still smaller than the sound speed at that position, the derivative of the velocity with respect to the radius is equal to 0, which means that starting from the critical radius, the solar wind will start to decelerate. This solution represents a family of solutions that we call subsonic breeze. The third family of solution represents the supersonic solar winds. If starting from a certain velocity, initial velocity, the solar wind accelerates in such a way that at the critical radius RC, the velocity of the wind corresponds to the sound speed, we obtain that the derivative of the velocity with respect to the radius will be always positive, and this will result in a wind that accelerates continuously, giving rise to a supersonic wind, which is represented by a family of solutions, of which one example is shown here. Let's now try to estimate some typical values for the solar wind. For example, let us estimate the critical radius. In order to do that, we need to know the sound speed, Vs, which is defined as, where Kb is the Boltzmann constant, which has this value in joules per Kelvin unit. Mu is the average weight of individual particles, which we express in kilograms, and where we have used 0.6 instead of 0.5 to take into account the fact that the plasma has a small fraction of helium, as we have seen in previous module. And we can assume a temperature of 1.5 million degrees Kelvin, which is a typical temperature for the solar corona, where the solar wind originates. Now we can plug these numbers into the formula and estimate the value of the sound speed. This results in a sound speed of approximately 1.4 10 to the 5th meter per second. We can now compute the value of the critical radius RC by plugging these numbers into this formula, where we have to remember that the total mass of the Sun is approximately 2 10 to the 30th kilogram, times the value of the gravitational constant, which is approximately 6.7 10 to the minus 11 cubic meters second minus 1 kilogram minus 1, we obtain that the critical radius RC is approximately 3.4 10 to the 9 meters, which correspond to approximately 4.5 times the radius of the Sun. This is the critical radius at which the solar wind becomes supersonic. Now, using these values, let's see how we can estimate the wind velocity close to where the solar wind originates and very far away from the Sun. Using the equation of motion and the isothermal hypothesis, we can integrate along flow lines and obtain that the square of the velocity divided by 2 plus the sound speed square times the logarithm of the density plus the gravitational energy is a constant of the motion. This equation is nothing else than a version of Bernoulli's theorem that you may use in very different fields. Let's now use the conservation of mass in spherical geometry that states that the product of the density times the velocity times the square of the radius is constant. The suffix 0 here indicates the starting values. If we now use the conservation of mass and we plug it into this equation and we integrate between the starting point and a radius r, we obtain the following. Where phi g naught is the gravitational energy at the starting point and phi g is the gravitational energy at the position r. Dividing by the sound speed, we have let's now define the following quantity, A, and note that A is adimensional. Now, using this definition and after some algebra, we obtain. Now, this equation allows to determine the initial speed of the solar wind, provided that we know the velocity v of the solar wind at a certain distance r. For the supersonic wind, we have seen that the supersonic wind becomes supersonic at the critical radius rc, and if we use the definition of A, we can obtain, if we now plug these values into this formula, we obtain, which determines the initial velocity of the solar wind as a function of the sound speed. We have seen that the critical radius rc is approximately 4.5 times the solar radius. This results in a parameter A, which is of the order of 10. If we now look for a solution where A is of the order of 10 in this formula, this in turn implies that the initial solar wind velocity divided by the sound speed is much smaller than 1. And therefore, we can obtain the final result, which provides the value of the starting solar wind velocity. If we now plug this result into the original Bernoulli's theorem, we obtain the value of the velocity far away from the Sun. I will not go into the details of the algebra, but I will recall the main formulas here. Now, using these results, let's plug in some numbers and let's compute the Sun mass loss rate due to the solar wind. First of all, let's compute the starting velocity for the supersonic wind. We find out that the starting supersonic solar wind velocity is approximately 100th times the sound speed in the solar corona. We can then compute the mass loss rate in the following way. Where ρ0 is the plasma density in the solar corona, which we approximate as 10 to the 14 times the mass of the proton. By plugging this number, we obtain that approximately 1.5 million tons of plasma are emitted in the solar wind per second, which is almost negligible with respect to the total mass of the Sun. We can also estimate the solar wind speed at the position of the Earth, recalling that one astronomical unit is approximately 214 times the radius of the Sun, which in our units will be 50 times the critical radius. If we plug the numbers into the previous formula, we obtain, which results in a solar wind speed at the distance of the Earth of approximately 560 km per second, which is a number which compares pretty well with the experimental measurement. Now, moving at about 500 km per second, the solar wind needs about 4 or 5 days to reach Earth, and many more months to reach the outermost planets. As the solar wind leaves the corona, due to the large magnetic Reynolds number, it picks up the local magnetic field, which is the field associated with sunspot and Sun's magnetic poles, and drags it into the space. The dragging of the magnetic field by the plasma is a result of the Flösenfrachs theorem that you have seen in Module 3G. The dragged magnetic field forms the interplanetary magnetic field. The interplanetary magnetic field is quite weak. At the Earth orbit is about 1/10,000 times the field at the Earth's surface. However, it exerts an extraordinary influence on the Earth magnetosphere. The magnetic field of the Earth provides an effective obstacle to the solar wind plasma. When it reaches the Earth orbit, the solar wind is quite rarefied, between 3 and 8 ions per cubic centimeter. The Earth magnetic field keeps the ions, clips the plasma out of the Earth by carving its own cavity in the solar wind. This region is called the magnetosphere, although it is not spherical. When it reaches the Earth magnetic field, the solar wind, as we have seen, is usually supersonic, and the magnetic field of the Earth creates a magnetic obstacle which creates a shock front where the plasma becomes subsonic. This region is called bow-shock region. The bow-shock region is approximately 17 km thick, and it is located at a distance of approximately 90,000 kilometers from Earth. Most of the solar wind plasma is heated and slowed down at the bow-shock and detour around the Earth. Some plasma of the solar wind penetrates inside the magnetic field of the Earth and form the so-called magnetosheath. The magnetosheath exerts a pressure on the Earth magnetic field. The region where the pressure of the magnetic field equals the pressure of the magnetic sheath, this is called the magnetopause. By dragging the magnetic field lines of the Earth magnetic field with it, the solar wind deforms the magnetic field lines and creates a magnetic neutral sheath where the magnetic field lines are opposite directed. As we have seen in previous modules, where opposite directed magnetic field lines come together, magnetic reconnection can take place if the magnetic field lines are pushed together strongly enough. One of the most important perturbations to the solar wind are coronal mass ejections, or in short, CMEs. During a coronal mass ejection, the Sun can eject 10 to the 12 up to 10 to the 13 kilograms of plasmas moving at speed of approximately 1,000 kilometers per second. These are strong perturbations to the solar wind, which can have profound consequences on Earth. By pushing together the magnetic field lines at the neutral sheath, reconnection can occur, and plasmas and electrons can be accelerated and reach down Earth, creating one of the most spectacular events on Earth, which is the aurora. This was the last module on applications of plasmas in astrophysics. You have learned that distant astrophysical objects like the Sun can have a profound influence on our environment. An example is how the solar wind shapes the magnetosphere around the Earth. Throughout the 5 modules, I have pointed out the importance of 3 major players in the dynamics of the universe: nuclear fusion, plasmas, and magnetic field. The complex interaction of all of these elements through dynamo and magnetic reconnection shapes our world. Plasma physics is of fundamental importance to advance the understanding of the universe we live in.